delighted now to welcome Professor Didier Queloz. He's the Jacksonian Professor of Natural Sciences and Professor of Physics in the Cavendish Laboratory. He's in Geneva, lucky thing, at the moment. And as you will have read in the background, he's made absolutely pioneering discoveries in exoplanets and is going to talk to us about that now, please.
Thank you, Mike, for this nice introduction. So let me share my screen with you.
That's great. Brilliant.
Good.
Thank you.
Fix it. Sorry for that. Okay, so I will be talking about what we call the Exoplanet Revolution, and there is pretty good reason why we call that revolution. So first, it is clearly this call that amazing explosion of discoveries that we have experienced in the last 25 years. And you see here an histogram that represent just the count of how many planets orbiting of the star has been identified, essentially by two techniques that doesn't see anything. We don't see the planet, but just is looking for the effect of the orbiting planet on the star. And the one in the red is called the radial velocity. We use the gravity that is pulling the star according to the orbit of the planet. And if you measure the speed of the star, or in the radial directions called radial velocity, you look for a change of this radial velocity, and the regular change of the radial velocity will give you a direct information about the mass of the planet. Another techniques that is well known, has been used by many satellites, is you are looking for an unlikely event when you have the orbit of the planet crossing the line of sight between you and the star. So for a very brief moment, when the planet will go in front of the star, it will be a kind of a shadow, and it will change the amount of flux or light that we receive from the star, and creates what we call a transit. So we call that the light curves, and from the light curve we detect the transit, and from that we derive the size of the planet. Now, this revolution is clearly, in a way, seen as an expansion of what was done almost 500 years ago with the Copernican revolution, when we tried to recenter the location of the Earth in the universe, in a sense that you project the planet, not only the one in the solar system, but on many other stars. But actually, it's even more profound than that, because we have built, essentially in the past 100 years, kind of an understanding of the solar system with our own planets. We build an understanding also of the formation scenarios, and we come up in a situation where essentially a lot we've learned from the solar system needs to be revisited and expanded. And to go through that with you, I need to give you a little bit of basics about what we know about planet formations. So these are the planet of the solar system. You would have recognized them. What is wonderful with this planet is you can study them in great detail. Despite the fact we have almost an infinite number of planets to study under the star, there is still a very strong interest to study in more detail the planet of our system, because that's the only one when we can really get into detail and possibly bring back some stuff from this planet back to Earth for more studies. Well, what is interesting, if you imagine you will cut the planet and look what is inside, especially the giant planet, is from the outside, they look like a big sphere of gas, in a sense, not very different from the sun. It's, in the case of Jupiter, which is 1,000 times less massive than the sun, we still have the same kind of gas you have in the sun, which is the hydrogen and a little bit of helium here. But what is interesting, and is also valid for what we call the ice giants like Uranus and Neptune, we have in the middle of the planet what is called a core, a solid core. And the reason for this core is very critical to the formation mechanism that is making the planet. Well, if you look at astrophysics, a lot of the astrophysics effect you can see in the nature are fully dominated by the gravity. And when you assemble object, you usually collapse object, and due to the gravity. You collapse object on something more massive, on core, on other object. And that's really the way you form a star. The star is formed by collapsing a big cloud of gas, and that is making the star. In the case of the planet, it's a rather different process, because in that case, we don't collapse the planet, we're building the planet from the inside to the outside. So in this case, we agglomerate the pieces together, from starting with the core and then bringing the rest on the top of it. It is called a core accretion mechanism. So this different mechanism is a reason why planets are different than the stars, and that's the reason why they have a core. Now, when you look at the solar system as it is today, and you not only look at the big planets you see, you look at all the tiny objects that we call the asteroids, and you imagine you just take a rocket, you fly perpendicular to the plane where most of these planets are located, you will see such a picture, which is a remnant of the origin of the solar system, which is from a disk-like structure, which is rotating in this case. And what you see from this structure is when you've been able to form the planet inside, and I will help you because this is the orbit of Jupiter you see in the middle, and the sun is sorry, it's in French. The sun is in the middle. This green patch of object you have is famously known as an asteroids belt that is called the Trans-Neptunian object, because they be on Neptunes. And they have been predicted early on as being a region where the formation of the planet were not able to be completed due to the nature of the disk. And this discovery of this mini object is not very late. The first of this object came in 92, and that was the reason why, Pluto was demoted from a planet to a dwarf planet, because we realized that Pluto belonged to this population of object. So this picture, disk-like structure of the planetary system was already identified more than 100 years ago by the mathematician Laplace, who came up with a boring idea of Kant that the origin of the system should be from a disk. Now, we know we have the tool right now to see this disk, and I would like you to pay attention to the size of the solar system here, which is expressed on unit of the distance between the sun and the Earth, which is 1 astronomical unit. In this case, here the scale is 50 astronomical unit. And what I will do, I will point the most powerful telescope that is existing on Earth right now to show you what looks like a disk when the star is very young, and at the same scale than the solar system. It's exactly the same. So you see they're matching pretty well on the top of each other. This is a star called HL Tau. This kind of picture is not done in the visible light. It's done in the millimetric light, same kind of wavelength you have in your microwave. And the reason why it's in such a far wavelength regime is because this object is very cold compared to the sun, for example. The temperature, if you compare it to the background, which is the universe, which is a few degrees Kelvin. This one is about 50 degree Kelvin. So you need 270 degree Kelvin to reach the 0 degree Celsius we're having these days with the snow around us. So this is a picture of what looks like a disk. And what you see here is any small particle which capture the light from the star and then is in a thermal equilibrium with the radiation that they receive with the star. It's like if you're sitting in front of the chimney and you have one of your face getting very, very warm. And then if you would look with infrared camera and yourself, you would see that the face facing the chimney will be shiny because it's more thermal energy being produced than your back that will be facing just the cold outside. So exactly the same here. So that's the radiations called the black body radiations for all the tiny particles you have here. So what you do see as well is there are a lot of structure, which is fascinating because in a way, this structure are telling you that there are something going on that is making the structure. We can think about having planet creating some of this structure, or the planet inside creating wave or ripple of gravity that will just, move across the disk from the inside to the outside, creating this this deep and trough that you see here on the image. So from this, I hope I convinced you that the origin of the system is from a disk, but the fact that we're talking about the disk, and the fact I'm showing you this picture, has a very deep consequences on the formation of the planet. So the first thing I would like you to remember right now is this is the picture that comes from the emission of the particle that usually we call dust or small particle here. There is another bit of the disk that you don't see here is the gas, because the gas is not visible in this picture, but you have to imagine there's a lot of gas as well. So to see a bit better here, I have to move to another picture. Pay attention to the unit as well. It's a bit twice bigger than I show you. These are two images of the same star. It's a very famous star called Beta Pictoris. It's a star from the southern hemisphere. On the top of the picture, this is a picture from the Hubble Space Telescopes, almost in invisible light, where we have masked the star, because the star will be extremely bright, extremely shiny, to enhance the disk that in that case you see just from the side. So you see the disk not like we see before from the top, essentially. In this case, we see the disk from a side. So there is something obvious about this picture, is how thin is the disk that you are looking at. So the disk, the matter, the solid matter of the disk is extremely thin, and in a way it is matching the situation you see with the planet of the solar system. You know that almost all the planets of the system are aligned. They're not strictly aligned, but they are almost aligned on the disk, on the plan of the solar systems. And we do have the situations which is due to the nature of the effect of the gravity of the Newton, the Kepler law of an orbiting object around a star. Well, what is fascinating on this picture, if I show you at the same scale, the same picture, when you try to see the gas. So it's the same telescope that called ALMA used for that, but in this case using for a gas which is the CO2. And when you look at the gas at the same scale, you see that the gas has a much more vertical extension than the thin disk of the solids. Well, there is a good reason for that. If you go on the top of a mountain and you drop a stone, the stone will just fall until the stone is reaching almost the bottom, the lowest position, the lowest possible position the stone can go. Well, if you take some gas with you on the top of the mountain, the gas is not going to fall. It will be automatically into a balance. There will be an equilibrium that will get in place. And this equilibrium, it's called the hydrostatic equilibrium, is the reason why you can go up to the mountain and still breathe. Of course, there is less gas, but there's still gas there. So by nature of the structure of the gas has a much more elongated structure. Now, if you pay attention to something else, you can ask yourself, how come the disk is more extended radially when you look at the solid particle you see on the top than the gas? The gas seems to stop abruptly to some distance. Well, the reason why is because the CO2, if you cool it enough, it's not a gas anymore. If you take the water, if you cool it enough, you get snow, and you know that these days. So the gas form of the nature of the material in the disk is changing, and it's becoming a particle. Because it's a particle, nothing will maintain the particle the same way vertically, and the particle will collapse. So you will end up with the situations that the material that used to be gas to some distance, which is usually qualified as snow line, because that's exactly the location when you start having solid particle for a given gas. Of course, it depends on the gas. Water, it will be at a given temperature. CO2, CO, NH2, NH3. You can imagine all the gas you can find, and there's quite a lot. Well, water being the most common gas you find in the universe. You will have a lot of falling material, a lot, way more than inside. This is the reason why it's pretty easy to form core of planet located outside the solar system. This is why we believe the core of Jupiter and Saturn was formed rapidly. And timing is key here, because if you collapse early on, you get a lot of material, you build a core. Once you get the core big enough, the core becomes attractive for anything around, and you have a situation when you attract all the gas which is around, not the same, but other gas around. And one of the gas you find plenty here that you never see as a solid gas, it's the hydrogen. So all the hydrogen around is captured by the core, and this is how you form giant planet. This is why everybody until 95 was looking for giant planet outside. Outside means it's going to take years for the planet to orbit around the star. So it was quite a surprise, you can imagine, for us and for the whole world when we announced that we have found a planet, but not at the location where you would expect a giant planet, but extremely close to the star. Now, what I want to do is a jump in time, and I'll show you a kind of an overview, what we know right now on the planet. There is plenty of way to see that, but the easy way is to just plot 3 parameters: the period of the orbiting planet, and then 2 parameters, the mass of the planet and the size of the planet. The unit of days for the period. For the mass, it's solar mass. For the size is, sorry, not solar, it's Earth mass. And for the radius, for the size of the planet, is Earth radius. So to help you, I have, let me just flip this. I have indicated Jupiter and then the Earth. And the reason why these 2 diagrams are different is in blue, these are planets found by transit, and in red, it's planet found by radial velocity. The reason why I do that, because we see a different picture depending on the techniques we're using here, and that's related to the sensitivity or the detection threshold of each of the techniques. Well, first, I draw your attention to all the objects that are sitting here, which is the mass of Jupiter and a few days of period, or the size of Jupiter and a few days of period. This is exactly where we found the first planet orbiting 51 Peg 25 years ago. This is what we call the hot Jupiter, because they are like Jupiter, but they are extremely close to the stars. They're very hot. Now, we have another set of objects, which is more expected, which are all these objects here that looks like kind of Jupiter. They are Jupiter mass, and they are orbiting in many years, orbiting the stars. Well, it took a long time to detect, to go from this one to this one, because it takes a lot of time. There is no Jupiter at long distance being found by transit, because it's just extremely unlikely that you are properly aligned. So the alignment needs to be so perfect for you to see a transit if the planet is far away, that becomes so unlikely. So you need so many planets of that kind to see one or two. This is why there is so few, and that's what you see here. There's very few. Now, the big surprise really came from this, kind of planet here. So you see the size is between the Earth and Neptune-ish, and the mass is between a few times or about the Earth mass and about the Neptune mass here. This object have no counterpart in the solar system. In a sense, they're all located at a distance of few days to maybe 1 or 2 weeks from the stars. And they have mass and size that doesn't fit into what we expect. You know, in the solar system, we have the Telluric planet and then there is giants. But here we're talking about objects that are slightly bigger or slightly more massive than the Earth. And we used to call them super Earth. Well, if you keep being more massive and bigger, they reach a regime when we start calling them mini Neptune. And then you can keep going up, and then you can find objects which become mini Saturn. So there is a whole range of objects that we have found that was essentially not expected. And this is a very incomplete picture, because what you need to add here is the kind of the boundary conditions that is limiting our view in a way on what we can see on the system, which is these two lines. Anything on the left side of these two lines is something we can detect with the current technology. Anything on the right side is very difficult. It's going to take a lot of time. And I'm sure you appreciate that the Earth and Venus is on the wrong side if you want the diagram. This is why, as of today, we have not found any proper twin of the Earth. We have found Earth mass object, we have found Earth size object, but they're way closer to what we've known. And the situation becomes even more fascinating when you start to do statistics here. So it's not easy to do on this diagram because there are a lot of threshold and systematic that needs to be corrected, and it's always a big debate how to do that. But essentially, the number I want you to remember for each of the category are the following. So the hot Jupiter is still a kind of a marginal set of planets. If you would see the star tonight, you need about 20 to 50 stars to find one hot Jupiter on the stars. It's pretty rare, still exists. So we had 150 stars in the survey we started 25 years ago. So we picked up 2 in a sample. So we were not really lucky. It was just the statistics, and we found what we had to find because we had the capability to do it. When you talk about Jupiter, it becomes a bit more tricky, and there's a big range because it depends how you decide where to cut. You see there's a lot of objects more bigger than Jupiter, and that was kind of a little bit of unexpected. There's also object how far you go in the direction. So depending the regime here, and there's a point when you reach the star, and there is an intermediate step called the Brown Dwarf. I'm going to enter through that. So this is a lot of uncertainty about this kind of object. But let's say 10 to 20% of the stars seems to have a Jupiter. So it's pretty interesting because it tells us like maybe this is a system that are a bit like us, while we only see a small bit of it, which is the fact there is a Jupiter. But the big surprise is when you look at this number. So there is about half of the stars and up to 80% of the stars that do have a system that we call super Earth in short orbit. Most of these planets come with other planets, and they tend to be qualified as compact super Earth system or compact mini Neptunes. And what is fascinating here, we have learned our way after Copernicus. Now we know that the solar system is not the majority in the universe. We only a small fraction of the many possibilities, because the most dominant geometry of planetary system is exactly that kind of system, which means object between the Earth and Neptune with orbit that would correspond to any orbit within the orbit of Mercury. So quite different. Of course, it opens the big debate. Why are we like we are? And that's something we still don't know. We still don't know exactly what is the key mechanism that prevent the system to end up like that. Essentially, the missing element in the formation of the planet I showed you before is when you form a planet in a disk, you have a lot of interaction between that disk and that planet. You also have interaction between planet and planet. And this combination of effect can easily move the location of the planet from its formation site, but can still remain on the outside. We're not breaking the theory in that respect, but the fact the planet will stay there is very unlikely. So if you start moving the planet to the star, well, some of the planet will just uh, dive into the star, will disappear. And we have some evidence that there may be in some stars hint that there's too much heavy material. It could be the fact that some star has digested some planet early on. And in most of the case, they stop because the disk, when you get closer, is not that efficient to promoting the idea that you migrate the planet in, and you end up with this system. So it's a fascinating situation we're encountering right now, because we have opened up a bit our mind on the fact that there is an intrinsic diversity. What is even more interesting is when you combine the mass and the size and you build up a diagram which is dealing with the density of the planet, and that show you the situation is way more confused than we think it is. Well, you see the mass of the planet on the horizontal axis and the size of the planet. Again, to help you, Jupiter, Saturn, and Neptune is here. So I want you to, all the point here are exoplanet, planet on other stars, where we have a direct measurements of the mass and the size. These are real data. That's a state of the art. I think there's a big database that we're using to collect all that. That was the situation 2 weeks ago. So it's very the situation right now. So you see all these objects which are slightly bigger than Jupiter. So the density is a bit less than Jupiter, which all the hot Jupiter, which is not a surprise because they receive so much energy. So they're a bit inflated. This is where you would expect a Jupiter if you could use the theory of the planet structure, and you can play around. If you increase the mass or decrease the mass, you will change a bit the size of the planet, and it explained pretty well Jupiter and Saturn. And you reach here the point when you have the mass of Neptune, and the exact nature, internal structure of Jupiter and Saturn is not applicable to Neptune, and we know why, because there is much more dense gas and very little hydrogen and helium on this planet. It's denser, that's why it's down here compared to the diagram. And to help you, I derive here what's called an hypothetical water bulk density planet. It's the planet that doesn't exist, but you imagine you make a planet only with water, with just small core with a lot of water, you would be along this line. Just to tell you that there is a kind of a plenty of way to build up the internal structure of the planet between the way you build Neptune here and a planet that would be denser with more water. And here you have the Earth. The Earth is 1 Earth radius, 1 Earth mass. If you increase the mass of the Earth and maintain the structure the same, I can go up, 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 up to a point here until I reach the Neptune's mass, but still not the Neptune density, still a rocky planet here. And you see that we have some planets that are matching this model. If you pay attention to that, you may see a kind of a small lack of planet here. It's called the planet of Wally. It's between the rocky planet and the planet are more alike, what's called mini Neptunes here that are made of gas. And we do believe this is real. And this is a connection of the formation mechanism and the fact that some of these planets are so close to the star that the star has evaporated the atmosphere of the planet. So the atmosphere of the planet could not retain its atmosphere. This is why it's now a bare rock planet without any atmosphere. So you see there is really a lot of interesting outcome way beyond what I mentioned only discovering. And if you want a new picture right now of the planet, well, we had the giant here, we had the ice giants I showed you before, we have the Earth. Well, we have to add quite a lot of diversity. There's object in between here, and we have this massive diversity of object. that you can easily fit between the mini Neptunes, dwarf giants, and gas dwarf, rocky super Earth, ocean planet, whatever you want to call them. So this is the true revolutions. We have changed the perspective. We are one amongst many. And of course, we would love to find a twin to understand how likely we can compare. So how are we going to make progress into that? We're going to use a light curve. This is a light curve of a star observed from space when there is a transit, and there's a time where the planet goes behind the star, which is called a secondary eclipse. The planet is in front of the star, the planet is behind. When you think about that and you zoom here, what you see is this 2 point here when the planet is behind. That's the only moment when you see the systems without any light coming from the planet. Whether it's a reflected light or whether it's a thermal emission from the planet, you don't see it because the planet is just behind the star. So you only see the star. So this is where the star would be. And the consequence of that is anything above that is a planet. This is why you see this called phase function here. This is why you see a drop. And from that, you can learn about the atmosphere, the nature of the atmosphere of the planet, even the dynamic of the atmosphere, the location of the hotspot. You can do a lot what is called weather of a planet. It seems incredible that right now we can study planet with so many detail in a way without seeing it, because we don't see it. I'm talking about the transiting system where I see the star. I don't see directly the planet. Tomorrow we will, because we're making a new generation of telescope. But today, all the studies, all we have learned is essentially almost without seeing a single planet. There's a couple of them for which we have images, but they're very extreme cases. Now, I would like to open a last chapter in this talk is the question of the habitability of life, because this is always there around and people keep talking about that when you talk about this, the topic of exoplanet. Well, let me introduce a concept that is around since almost the end of the 60s here, which is this is what's called the habitable zone. So you can compute a region on the orbit on the solar system where you can move the Earth around and still retain the liquid water situations. It's called a liquid water minimum condition. So if you go too far away, you move out, you will decrease the temperature, and there is a point when you enter into a regime which is called a snowball regime, and the water cannot be liquid anymore. It becomes a completely frozen planet. This is the end of it. This defines the upper boundary, which is this one in this case, next to Mars. When you move inside, you have the opposite scenario. The temperature rise up. You are going to start losing the water by evaporations and the atmosphere as well. And this is the inner boundary. Now, of course, you can play with this boundary depending on the chemistry of the atmosphere. You can add a bit of CO2 like we're doing today quite efficiently. And by doing that, of course, you're changing the temperature and you can move away giving the same temperature. So you can play around with the chemistry of the atmosphere, but essentially defines boundary conditions. What is fascinating with these boundary conditions is essentially all the planets we have found are way too close right now to be within the habitable zone. There's very few that would sit in because we're looking at planet orbiting star like the sun. Well, instead of changing the atmosphere of the planet, you can change the sun. And using, you take a sun which is a little bit smaller, it will be a little bit dimmer. So it means if you want to sense the same amount of flux, you will have to get closer. So this is why the habitable zone is getting closer. When you decrease the mass of the stars, the star becomes dimmer. Well, what is fascinating, and when you do that, you cross all this many planets that we've seen. So we have found, and there are a lot of planets at short distance within weeks. So it means that technically speaking, we will have quite a lot of planets orbiting smaller stars that will fit the criteria of liquid water minimum conditions and have the possibility to have a sustained atmosphere and then a sustained liquid water at the surface of the planet. It's a fascinating prospect, and it has pushed a lot of the studies right now and the astronomers to look for planets on small stars. It's a very extreme case that went to the press at the time. It's a TRAPPIST-1 planetary system. It's a very small star. The star is extremely dim, and is such a small star that the planetary system that was found is 7 planets on very short orbit. This planet, which is planet H, is at the same distance that we found 25 years ago, 51 Peg. That was 20 times closer than the Earth to Sun distance. So this is very, very narrow. If you have this to scale to the solar system here, that will be there, 5% of that distance here. But because the planet are orbiting a star very dim, the light coming, you have to rescale it accordingly. And you have, in a way, a mini-scale version of the solar system in terms of thermal behavior. And planet EF and G are within the habitable zone definitions that I described to you. Now, it doesn't say anything about whether the atmosphere of this one, but I hope I convinced you that we are way to prompt them and to study them by the technique I showed you before. Now, the question I would like to discuss briefly is whatever we can expect life on TRAPPIST, and what are the prospects to understand the origin of life. In a way, the origin of life and the factor of life on planet is connected to the core purpose of studying this planet and trying to understand, finding other Earth twin, and to see whether there is similar mechanism elsewhere. I would like to just share with you some very recent work on that. Well, the first thing I'd like to tell you is to face the reality. If you imagine that, but looking at the oxygen, because very often the oxygen, you know, is one of the main products of life, is a way to find life. I think we should stop short at this idea, because this is a couple of scenarios, different atmosphere for different scenario here, that tend to demonstrate visually that you can easily produce molecule of oxygen and water without having a planet that meet the criteria for life, just by the interaction you have with the UV flux and other gas you have on the atmosphere and the geophysics pattern of the atmosphere that create it. So there's plenty of way to create oxygen and water. And the fact oxygen is everywhere, and the fact that, oxygen is created very early on by the stars, and hydrogen is everywhere. There is no more common molecule than water. You point any telescopes that's sensitive to water outside the atmosphere to globular clusters on young systems, you will find water in it because it's everywhere. So the fact you have water and oxygen is not enough. You need to find another way to understand the origin of life and the possibility of life. Of course, you can set the requirement very high and look for exactly what you know, which is exactly a copy of the Earth. Of course, if you find exactly the kind of molecule you have in the Earth, you can find out that maybe we have here a similar copy here. But given the diversity we're experiencing right now on the planet, and given we are scientists and we should be more open-minded to surprises, I think we should give up on that and try to find another approach. So quite recently, a lot of progress has been made on a different programs, which is, instead of looking for life, we should be looking for conditions for life. It's more than habitability. It's, you want to look for what are the key ingredients that you should be looking at if you want to ask the question, is there life on this planet? And it goes down to what's called the prebiotic chemistry, which is going on to the chemistry that is the first step that will enable the formation of life later on. Well, there is something as a physicist which is striking, is when you study physics, you learn the standard model with all the particles. There is, in a way, a standard model in the life. These are the amino acids. These are the building blocks that is being used by life. Now, you can just see that as a random process, but you could see that as very profound. The reason why these amino acids are being used is there is a very good reason for that. And I tend to like this approach because we can try to make prediction with that. And one prediction is there are conditions that is creating only these amino acids, and only this 21 amino acid we have, the 20 amino acid we have here. And that's the reason why life have been using them, because they were the only available ingredients. It's like if you want to build a house in Sweden, you better do that with wood, because there's plenty of wood. If you want to do that in Canary Island, you better do your house in stone. Good luck to find trees in Canary Islands. It's exactly the same idea here. And what has completely changed on that topic is 5 years ago, a mini revolution coming from the chemistry side is a real synthetical model, chemistry model, that is able to create these amino acids. So I would direct you to this recent paper on that. There is a couple of people in Cambridge working on that. That was, for me, one of the main motivations to just come to this place, is to work with these people. John Sutherland is very famously known for this. It's called the Universal Life Model. This model is not considering the bottom of the oceans as the origin, is using a complete different approach. We said, let's find the chemistry, the chemical reaction that is making possible. Let's try to demonstrate that we know the chemistry reactions, and let's try to understand the consequences on the geophysics. Well, they come up with something amazingly simple that is matching the geophysics of an early Earth. Is to make it work, you need water. Okay, that was understood. Nobody was challenging that part. SO3, there's plenty of it through the volcanic activity, which is implicit for life. You need some volcanic activity to kickstart life. HCN is not something you really think at once when you think about life, because I would not recommend to play with HCN. You will just die. Cyanuric acid is a very dangerous lethal gas. But there are plenty of HCN in comet. The reason why, because C, N, and H is found plenty into the interstellar space. Under UV flux, you create HCN into comets quite a lot. And then comet falling on Earth bring a lot of HCN, especially in the early stage when there has been tons of comet arriving at the early stage of the formation of the systems, because it was the nature of the formation of the system, planetary system. So a lot of HCN coming up, and that is very active and needed for the early steps. The atmosphere is pretty boring in a way. It's very different from the early attempt to create life with the famous experiment, Milne experiment. Because they were the implicit idea is there were a lot of energy, a highly reduced atmosphere, which we know was not the case. We know the atmosphere was not reduced. When you form a planet, you have a lot of CO2. It's a very pretty much neutral atmosphere. No energy really to make a great chemistry from that. So we need something else, and something else is UV radiation. So UV radiation comes for free from light, and what is fascinating in this model is you need a minimum of UV radiation, because if you don't get enough, you're making a nice chemistry, which may be doing a nice perfume, but is not going to create the 20 amino acids. So there is a threshold that you define with the UV flux, which is needed. When I learned about this, I've been talking with this guy doing this model, and I asked them as an astrophysicist, did you check whether your model was working for the solar system? And they look at me, I say, well, we don't know. We have been using an UV lamp from our lab. But I say, well, I mean the sun. Did you try to compute the UV flux from the sun at the early stage of the formation of the system? And they say, we don't know how to do that. And then started a big collaboration with this guy that led to this paper, led by one of my collaborators, Paul Rimmer, that tried to understand whether it works. And this led to an additional element here that we call the Arbiogenesis Zone that define the minimum conditions to create these UV radiations massive enough to create this reaction. So on the line, you see the period again, and then you see the temperature of the star. You see the habitable zone that get closer to the period of the planet. So the short period planet with the TRAPPIST systems, and then the farther planet away. And what you learn from this Arbiogenesis zone is a bit depressing in a way, is it doesn't work for most of the small stars because they don't produce enough UV radiations to create this chemistry. So the consequence of that is there may be life on the system, but if you believe to this formulation of the origin of life, it is not the life that we have in our solar system. Certainly not the same amino acid and maybe not the same kind of structure for life. So this has triggered a lot of interest when people are start to realize that maybe the key to understand life is being a better understanding of the structure on the surface of the planet, which is something we can go. And then geophysicists got quite fascinating by that. And we have this very complex, I don't want to go around that, but describe the various phases of the structure of the Earth with the origin of the atmosphere. But the reason why I show you that is just to give you an idea that if you want to solve the question of life, you have to solve at the same time a lot of different parameters: the origin, the planetology, the evolution of the planetology, the delivery from the space, then the interaction with the atmosphere you have, the prebiotic atmosphere and UV flux, and then after the prebiotic chemistry and the beginning of life. It is an intrinsically multidisciplinary problems, which is why it's difficult, because it's difficult to get funded for something which is crossing a lot of boundaries anywhere in the world. Well, we're lucky we get know a lot of private money helping us to develop this program, and hopefully we get more supported by University of Cambridge into that. And my last slide, still to give you a little bit what I understand by life as a physicist, just to make sure I don't enter into an argument with biologists later on. I see that as a kind of a diagram when you see the chemistry complexity growing, and I said chemistry because I think life is about chemistry with time. So it's a diagram which is not really linear. So people making predictions of a linear growth of life, I think they're wrong, because I don't see at all that as a linear process. I think it's closer to chaotic here and a bit similar to the talk we've seen before. But the key ingredient is there is a regime when you would qualify the object as alive. I have no idea where is this threshold, but there must be a threshold. Then you start to be directed by the biology and the evolution, innovation by evolution is the one that is driven the biology. But before you reach that stage, and this is a challenge, you have to do a team play between astrophysics, geophysics, prebiotic chemistry, and then the beginning of the macromolecules. How do you do that? By small improvements, by tiny change you have, making just innovation, which is related to the fact you have a lot of deposit of some material, you have a special event of geophysics, you have something evolving that making the conditions pretty good. With some moment where you don't really innovate very much because you just consolidate. And that's kind of this steady path here that hopefully will drives to the origin of life. So as an astrophysicist here, what I find fascinating right now is we have two ends of the problem. We have the capability to study in great detail the chemistry of life on Earth and maybe create life into the labs. We have the capability to go to the planet of the solar systems. We're going to Mars, we're going to bring back stuff and find maybe some element of some geophysical evidence of life or some prebiotic chemistry. I'm not even hoping for life, but some evidence that something has happened. And then we have an infinite number of planets to study with the difficulty that we'll never bring back stuff. But we have the capability to remote observe it, to compare and to study a lot and to learn a lot about the geophysics, hopefully I convince you, and the atmosphere of this planet. All together, that should hopefully give us a good picture, not only that we're not alone as a planetary system in the universe, but there is plenty of aliveness a bit everywhere in the universe, whatever you define exactly by being alive and aliveness. So I stop here and thank you very much.
Well, Professor Queloz, that was utterly fascinating. I suspect there may be one or two questions, and you're kind enough to say you would take them. And first of all, Jonathan Milner asks, and you may have hinted at the answer to this, but are there any Earth-like planets discovered at all yet?
Yeah, that's what I mentioned. I think there is lots of a little bit of a game here when there is announcement. So there are quite a lot of Earth-size planet. There's quite a lot of Earth mass planet. There are planets that seems to have an Earth like density, kind of bulk density, but we don't have a planet that have for sure characteristic that would qualify as a rocky planet at a distance that would fit within the habitable zone right now. We have maybe some hope that some may be, but we don't have the clear evidence because we are missing one of the parameters to be conclusive. But we have to admit right now that while the focus was to find a planet, a solar system like the Earth at the beginning, we have utterly failed on that. But that was a piece of luck because we've been lucky because nature has been very nice with us because they have made available so many other planets along the way. So this has helped the field to grow so so tremendously. So right now we're reaching a level of technology where we will be able to find what's called Earth twin, or quite often they call Goldilocks planets because perfectly suitable for life in a sense compared to the Earth.
Fantastic. So just a quick reminder of for the audience, I'm delighted to read out your questions, and I'll do that now. But if you would like to speak to us and be on the telly, just put your hand up, and Valerie will bring you in as she has a gap. But let me go on with the next written question, which is by Mel from Worthing Astronomy Society, who says, with the launch of the James Webb Telescope and the recent stunning image of the black hole at the center of a galaxy in mind, how long do you think it will be before we obtain an Earthrise type image of an exoplanet like Kepler 22b, for example?
Well, image of a small planet is still amazingly difficult. And the problem is very simple. It's not because the planet is faint, because the star is bright. That's really the main issue here. And that creates a lot of problems here that require very, very large telescopes. So the kind of size of telescope you would need in space to see a planet, I'm not sure if Kepler 22b is the best example, but let's say something that is even kind of like the Earth. It's about a telescope that doesn't exist right now because we're talking about a telescope about 20 meter size diameter. So on the ground, we're building that size, and we do think that there may be some hope with a lot of tricks to do something on a nearby object, a nearby stars, which is Proxima Centauri. Now, what I would like to say is I understand the appeal of an image. Nothing is better than an image, but people would be disappointed because it will still be 1 pixel. And what matters here for the astronomers is not the fact you have an image. I mean, frankly, we just don't care about the image. It's the capability to retrieve the flux coming from the planet, because this is the Holy Grail, because this is where is sitting the detail about the geophysics and the atmosphere conditions of the planet. And this is what you really want to do here. Now, the point is, if you get an image, if you get a pixel, you get it. And then you can study this, and you have plenty of opportunity to do that. And people are designing equipment for the future. James Webb Space Telescope will not do that. But the James Webb can do something different, which is using this capability I described of the fact when you have a transiting planet, you can study the flux coming from the planet by subtracting the flux from the star. So we don't see the planet. And my claim is using the James Webb Telescope and a couple of objects we have, in the next 10 years, we will have planet that will be rocky, where we will have an evidence of at least a thick atmosphere. An atmosphere thin like the Earth is too difficult to find because it's too narrow, too small. But if you imagine an Earth with a very thick atmosphere of the order of hundreds of kilometers, for example, it would be challenging for life, but that would be fascinating for geophysics to understand what are the conditions of such a planet. And this is going to happen, I'm pretty sure. And who knows? We may have big surprises. And that is something which is fascinating in science, is you can come to your office believing you understood everything, and bang, you learn something that you were not expecting, and you are having an amazing day by trying to catch up what's going on. So who knows? But James Webb is certainly not the magic one for that, but that's a big step forwards for us. I agree, the black hole picture was just amazing. I was amazed.
Great, thank you. And now, at the risk of lapsing into space jargon, I think we have Annabelle about to come on screen. Annabelle, are you there?
Yes. It was a mistake, actually, but I will ask a question. Can you hear me?
Yes.
Yes. I would wonder whether, for the kind of life that certainly is sort of like more like us, like mammals and so on, I would wonder whether it's possible that electromagnetism may play a part.
What do you mean? To make life, or to signal life? What do you mean here? You mean a civilization detection?
To make life, to make life, at least
to make life,
intelligent life, let's say.
Okay, so, well, you know, when I'm talking about life, to me, I don't even enter into the kind of life, because I don't think we qualify as intelligent life more than a dolphin. We definitely are a product of life which is able to leave our planet. That makes us, in a way, special. Whether we are intelligent, I don't know, but certainly we can do so. No, this is, I would say, a different topic, which is not my topic of interest right now, because I think the life as I see it on Earth is unique and single. There is only one life on Earth. We're all the same. There is no difference in terms of where you are alive, which make you different from a flower. We have the same way to be built. We build on the same principle. The fact you assemble on many cells, and the fact you so much diversity yourself, and the fact you mammal all this, from the evolution of life, from the origin of life, to me is a detail for the onset of life. Of course, it's a fascinating topic for the biology, whether when you have life, whether you always evolve into something more complicated, always you form a cell, you have a multicellular, and then you start to specialize, and then you have a completed entity. But to me, the Earth is one alive system. The question is whether you have another planet, would you have a similar life system? Is it built on the same principle? Or is it such a special to get alive? Or are we so special in a chemistry, in a way, that they are the only way that we can have a sustained evolutions? Because maybe you can imagine life can just appear and then disappear. So that's a completely another topic, and it's fascinating as well. But I think, you know, there are some people that are making the step without any problem, and Carl Sagan was one of the very first one to set the scenery, and that I said, well, look, if there are life everywhere, and I can't believe life has not evolved, and then in similar way than us, then we should have plenty of civilization everywhere, so it should be visible. Let's look at civilizations, and let's listen, radio, ET, all this kind of stuff. This is a perfectly acceptable point to do that, but it doesn't answer the question about the origin of life and the diversity of life, because maybe you have 1 out of 1 billion of the many expression of life that is leading to something like an evolution like us. And there is all the rest that creates life, but doesn't produce this enough aliveness, or some level of aliveness, but never evolved further. And I think that is what's quite fascinating to understand as a physicist. And I'm trying to help a little bit in the direction.
Thank you. And there's a slightly related question from Camilla Benfield, who says, what drives the innovation towards aliveness before the alive threshold in your last diagram? Anything, or just stochasticity?
I think it's stochasticity, but it's the game here is always the same. If you want the chemistry to be efficient, you better be good. Because otherwise, you imagine you have two processes that are using the same ingredient, and they're very similar. So one process is a key steps that is needed to reach some more level of aliveness. The other one is a great process that is making perfume and has no connection at all with life. Well, what makes the difference is the fact that one of them is more efficient than the other one. And that is the interesting connection that we need to build right now with the molecular biologists. We're trying to understand what is the chain of reaction that you need to have to create the most, the clear path for life. Of course, we don't know the answer. The fact that they produce amino acid, it's a long way until they produce life, because amino acid is not alive at all. But hoping that this is the way forwards, the idea is in the lab, sooner or later, these teams are going to make life in a similar way that the people working with the atoms 100 years ago started to play with the atoms, that discovered the radioactivity, and sooner or later, they recreated what is happening into the sun. So sooner or later, we're going to make life. In a way, we will have all the ingredients to really be like a god. We have the power of the fire, and we have the power of creating life. And it's going to happen, because I don't see why it would not happen. Now, the question is, to create this path, there is a minimum conditions. I mentioned the UV flux because that was an obvious thing to test, and that was a prediction. So I was so happy when we came up to the conclusion that it does work. So this, because the network they have assembled, I would have shown that the UV flux that was available at the time of the origin of the solar system was not enough, it could have been a nice theory, but it would have been a theory nicely to be trash because it's not relevant. It survived this first test. So there will be other tests. And I think the idea is trying to find a series of tests that you can relate to the geophysical condition, because life has to happen in the dirty conditions, essentially on the surface of the planet, with river and flow and pound and whatever you can think about it. And we can make testable, prediction on that. And my hope is by improving our capability to study the atmosphere and the geophysical conditions of planet that would look like the Earth, we will increase our understanding of this minimum condition that can drive life. And when all will come together, we may have some kind of hint of an answer. And I do predict this is the beginning of a new field of research. Like in the 60s, the molecular biology was kickstarted by the DNA that was just imaged by physicists using X-ray imaging techniques. I think today, the combination of the geophysics, astrophysics, and molecular biology are creating or paving the way of a new field of research, which is addressing the question of the origin of life in a more universal way.
Great, thank you. And John Cook would like to come on screen. John, please.
Hello, thank you. That was a fascinating talk. It's an amazing re-evaluation of our place in the universe, I think. I'd like to return to astrophysics. You showed us a really dazzling array of different kinds of planets, the water worlds, the ice worlds. What is there something that leads to these happening in a particular solar system? Ours is a particular solar system, but these other ones, is it the nature of the starting material that we come from supernovae debris? Do we know that this is uniform debris throughout all the areas where solar systems are being formed, or does one particular place rich in heavy metals lead to heavy elements, lead to Earth-like planets? Or
yeah, I mean, this is a very, very good question. I mean, frankly, we don't have a clear answer yet, but what you said is perfectly true. All these ingredients are created into stars, and there are certainly regions that are more enriched in what called metallic element, which is not the truly metallic for chemists in astrophysics. And it certainly plays a role, like certainly plays a role if you form a cluster of star at the origin very compact or something a bit more loose, because you will have more bigger stars, and bigger star can certainly, with the amount of energy of big stars, or even supernova that happens very quickly, blow out completely the material around the stars and maybe stimulate the formations of other stars and creating other planetary systems. So I think certainly the nature of the disk is critical, but there is some number that is worth to keep in mind. If you just do the math and look how much material is stored right now in the solar systems. So in terms of gas, all the gas is essentially into Jupiter and Saturn, which is, I give you 0.2% of the gas is there. So it's very tiny, it's almost nothing compared to what is into the stars. If you look at the solid particle, we're only talking at a fraction of this gas amount that is there. And it's almost nothing that you need to form a planet. The mass of the Earth is 300,000 times less than the sun. So there's really this ratio that you have, which is significant here. So it's not about the material around. We do think that essentially in all the disk, you have enough material to form planet. There's plenty of material to form planet. The question is, do you have the time to make it before everything is going to vanish? So it's kind of a race against the time where the whole disk structure is going to vanish, because the structure of the disk is so light that it has any intrinsic way to get sustained. It is blown, essentially is blown out by the star, even if the star doesn't create a lot of flux. So it's a timing element, and this timing element is making the planet formation. But it is expected that in the case of the hot Jupiter, we have seen systematic pattern between the amount of heavy metallic element in the star, right? And the fact you have a hot Jupiter, which is, the assumption is because the star has more heavy element, it means that maybe the planetary disk around had also similarly more heavy element. And then this has enhanced or facilitated or made the formation of hot Jupiter quicker. And this is why you have hot Jupiter at the end. So it is a very complex series of events with big steps that we poorly understand, like these famous steps called the meter problem, where when you form an object that reaches about a meter size in the solar system, is very easily dragged toward the star. So it disappears entirely because of the drag against the gas. So you have to create very, very quick something bigger that it doesn't see anymore the hand wing from the gas, and it is going to stay essentially, or lose little speed and then angular momentum and drifting down. So this race and the combination of the material is the reason. At the end, it may be just a highly stochastic process when there is so many parameters that goes into where the fact you have a nearby planet triggers something to the next one, and then you end up with a configuration which is different. So this is maybe why there is a diversity, similarly to the weather. So the weather is a single equation, it's Navier-Stokes. We understand pretty much the chemistry, we understand everything. It's one single equation. Well, it produces a kind of an amazing diversity of event, depending the kind of illumination you have on Earth and the global circulation you have on the sphere and the oceans. Quite fascinating, or you can change the outcome of the weather, right? Well, maybe the same is going on in the planet with about the same kind of idea, the same kind of basic equation you have, because a tiny change will have a dramatic consequence at the end. So that's a way we try to understand that right now. But we're still frustrated not to be able to assess the likelihood of a planetary system like our own, to understand how likely we are and how likely is a system like our own.
Thank you.
Well, Professor Queloz, thank you. That's the right place to end, I think. You've given us an absolutely fascinating tour d'horizon, dare I say, of the current state of the art. And we've all learned a huge amount, but you leave us with the clear understanding that there is still more for us to understand. There are one or two other questions which are a bit technical, and I dare to hope that if people dropped you a quick email and said they were listening to your lecture this evening, you might be willing to give them a quick answer. But really, we shouldn't really trespass any more on your time. It's 10 o'clock there in Geneva. We couldn't have had a more fascinating evening. I thank you so much. Thanks also to Francisco. That's all for this evening, ladies and gentlemen. Thank you very much. It's been a great session.
Thank you very much.